This is our interim presentation for our project, Robotic Gripper. We are Matt, Andrea, Jacob, Brian, and Sophia. We're Team 2. We'll firstly introduce our project's product and what's the target market. After that, we'll move on to the details of products, functions, and how it is assembled, the bill of materials, and we'll wrap up this presentation with product family. The robotic gripper is basically used to pick up and grip items as a replacement of hands. It's used in electronics and technology industry mostly to handle small parts and tools makes those processed more precisely. The production quantity is about 50,000 a year. By a lot of research and reports, this industry has been growing steadily in past 3 years, and it will going to grow for the next 5 years. In this project, we will focus on redesigning the finger. Our primary target customers are electronics and technology industry. In this industry, they need the gripper to realize holding lightweight tools and parts automatically and precisely. And the secondary customers would be medical and cosmetic industry. It also needs the robotic gripper to automatically build small assemblies, pick up and replace small parts. Here's the assembly drawings CAD file that shows all components and their names on it.
This is the fast diagram for the gripper finger. The main function of the finger is to grip objects. To attain this, the finger needs to stabilize objects by increasing friction and exert pressure. It also needs to transmit motion, which is done by allow translation and transmit power. To assure the dependability of the finger, its structure needs to be stabilized. Last, to enhance the product, we decided that there will be interchangeable attachments for the finger. For the function component mapping, all the screws and washers are used to stabilize the finger structure. All the pins are used for stabilizing the structure, allowing translation, and also transmitting power. The races of the finger are used to allow translation and transmit power. The inner brace cover and the rubber pad are used to increase the friction to grip objects. The rubber pad and plastic grip piece are used to exert pressure on objects. Finally, the plastic grip piece can be interchangeable.
Here we have the Fishman assembly diagrams for two possible assembly sequences. Sequence 1 is bottom up, so we start with the bottom cover and then build our way up to the top cover. Sequence 2 delays the cover placement, so it starts with the inner and outer support braces and then places the covers near the end. Here's a table comparing the two sequences. Sequence 1 is better in terms of handling and locating parts, since you only need a single position of the assembly for the whole assembly process. While sequence 2, you need to turn the assembly around a couple of times. However, sequence 2 is better in terms of fastening and joining, since it gives that extra flexibility when you move around the assembly. And it is also easier to test the sub-assembly, since you're assembling all the moving components first, so you can test that before attaching the covers. Sequence 1 got a total of 12 points, while sequence 2 got a total of 10 points.
Here's our bill of materials, which lists each component in the finger assembly, as well as the cost to produce it. We assumed a $60 an hour rate to operate the machinery for the parts, a $20 an hour manual assembly labor rate for the manual assembly. We also assumed an initial tooling cost of $50,000 for each custom component. So this totaled out to a total manufacturing cost of $37, which was much less than the $5,000 retail price of the gripper arm. Some other costs that this retail price might cover would be the rest of the gripper arm components, which are not listed in the finger assembly, as well as the cost to produce the software for the gripper. Here in this table, we sort some of the components by relative cost and functional importance. Most of our important high-cost pieces were the custom components, while the low-cost pieces were mostly fasteners and standard components.
Here is a functional differentiation table showing the similarities and differences in our product design for both of our product variants. Most of the functions are the same between both of our product variants that target different customer bases. The only difference is in an interchangeable attachment. Here's a component commonality table for our product varieties. There's a lot of similarities in the components between both of our products in our family, the only difference being in the plastic grip piece and the rubber pad. Here are some images showing our two different product varieties. The differences between the two varieties are in the shape of the grip piece on the finger of the gripper. The secondary variety has more of an angular shape in the gripper, as shown in the images here. And this design is meant to allow the gripper to more easily pick up rounded or circular items and objects. Here is one of the assembly sequences we have for our products, and the next is a modified assembly sequence that better implements delayed differentiation.